The afternoon is going to be given by Giuseppe Lodato. He's going to tell us about planetesimal formation in self-gravitating protostellar disks.
Thank you. Okay, first I would like to start by mentioning a number of people who have, to various degrees, contributed to the work that I'm going to present today. And first of all, I would like to mention Peter Cossins, who's my student in Leicester, who has actually done most of the work. And then, of course, there is Cathy Clark here in Cambridge, and my long-term collaborators, well, Ken Rice and Phil Armitage. So yeah, I've been asked to speak about the dynamics of solids in a self-gravitating disk. However, obviously, in order to understand the dynamics of solids, we need first also to discuss what is the dynamics of gas in a self-gravitating disk. So actually, in this talk, I'm going to cover both. So that's more or less a summary of what I'm going to speak about today. Well, first of all, I'm going to ask what are the conditions for the disk to be gravitationally unstable, and I'm going to try to understand whether actual protostellar disks are or are not, or in which parameters, for which parameters are these disks going to be gravitationally unstable. And then I'm going to give a little bit of discussion of what is the dynamics of the gas in these disks. I'm going to briefly touch on the issue of fragmentation, although this is not really the main topic of this talk at all. But then I'm going to also discuss about whether this issue that has been brought up yesterday in a couple of talks, whether the transport induced by gravitational instabilities can be described in terms of a local framework or not. And finally, in the last part of the talk, I'm going to finally start addressing the dynamics of solids. I'm going to describe a number of simulations that we have done quite a few years ago now on the formation of planetesimals in the spiral arms. And finally, and that's the most recent thing, I want to discuss these kind of processes in the context of more realistic global models for self-gravitating disks. So let me start with the first point. What are the conditions for instability? We all know about that, but I'm just going to go through it quickly. So we know quite well that this Q parameter regulates the linear stability of axisymmetric disturbances in a self-gravitating disk. And we see that this is proportional to the sound speed and inversely proportional to the surface density of the disk, which automatically means that in order for the disk to be unstable, we need a cold disk or a massive one. Here, kappa is the epicyclic frequency. In all of the disks that I'm going to consider, actually, the disks are going to be almost Keplerian, so we can replace kappa with omega. And if that holds, now there is a very interesting, well, there is an equivalent formulation of the same condition, which is this other one. So in order for the disk to be unstable, we need the ratio between the disk mass and this should be m star. So the ratio between the disk mass and the stellar mass should be larger than the aspect ratio h upon r. And well, here I just want to point out that this, when I say m disk here, this really means sigma r squared, okay, at a given radial location, which might not be a good estimate of the total disk mass if the surface density departs strongly from a power law. So it's essentially sigma r squared over m should be larger than h upon r. So in order to understand whether, if you take a protostellar disk, this is going to be unstable, we need to have estimates of h upon r, which are related to the temperature of the disk, and of m disk over m star. So what are the masses and aspect ratio in actual protostellar disks? So for the aspect ratio, I'm going to, well, just to give you an idea, this doesn't mean to be really precise, but I just take these numbers here that actually were quoted in Chang and Yudin. This is basically a simple Chang and Goldreich model for an irradiated disk. And you can see that h upon r is of order of a few percent with a rather shallow dependence on radius. So let's say that is, say, between 0.02 and 0.06. It might vary a little bit if you consider also self-heating of the disk through viscosity. But let's say that we need disk masses which are of the order of roughly 5% of the stellar mass in order to be linearly unstable. So the question is then, what is the mass protostellar disks. And here, this gets a little bit problematic to understand that from an observational point of view, because protostellar disk masses are quite difficult to measure. In the previous meeting that we had in August, actually, Lee Hartman made a big point about possible uncertainties in dust opacities, which would lead to a substantial underestimate of the disk mass taken from dust emission. However, let's for a moment forget about that and see what kind of masses do we get based on dust emission. And so basically, some of the most extensive samples probably are the ones collected by Andrews and Williams, 2005 and 2007, in Taurus and Ophiuchus. Actually, Sean Andrews gave me his data, so I can plot his actual data here. So that's the distribution of disk masses in units of solar mass for the class 2 objects that they had in their sample. So these are T Tauri stars. And this line, which I put here, is at 4%. So above this line is more than 4% of a solar mass. And this already shows you that in general the T Tauri mass, the disk in T Tauri stars are not very massive, but you can already see that the upper end of the distribution is already in a regime which would be linearly unstable. It's just a handful of them, so it doesn't really tell us much. But I would like to point out that this is M disk over M sun, which is not what we are looking for. Actually, what we're interested in is M disk over M star. So I can take the stellar masses again from the sample of Andrews and Williams and plot M disk over M star rather than M disk over M sun, and basically that's what I get. So the distribution shifts a little bit to the right. That's because essentially the typical stellar masses are below a solar mass. So actually, the fraction of stars of disks that you have in this upper end of the distribution is a bit higher. Still not much though. But let's go back to the first plot that I showed. So M disk over M sun, and let's compare that to the same distribution, but in the case where rather than taking class 2 objects, T Tauri like objects, we go a bit earlier in time. So we look at class 1 objects, and that's what we find. Again, the distribution shifts to the right, which again means that a larger fraction of these objects are going to be linearly unstable. Now it would be nice if this peak actually was on the other side. But in this respect, actually, it's interesting because even for these class 1 objects, the same argument applies. This is M disk over M sun. What we would really need to check is M disk over M star. Unfortunately, for class 1 objects, it's a bit more difficult to get accurate stellar masses, and indeed, Sean Andrews was reluctant in giving me any numbers for their stellar masses in this class 1 phase. But arguably, the effect is going to be similar to the one that was shown for the T Tauri case, if not larger, because these are younger objects. Maybe you expect to be even less massive than the T Tauri sample. So maybe there is some hope to move it a little bit farther to the right, so that the peak actually moves on the other side. On top of that, I should remember that all this is without taking into account the possible underestimate of these masses based on dust on the uncertainties in the dust emission. So basically, actually, so it's likely that all these numbers that are quoted here are just lower limits to the actual disk masses, and therefore I'm pretty confident that at least in the class 1 phase, a large fraction of these disks are going to be gravitationally unstable. There's also another issue which is connected.
Don't you expect class 1 disk to be hotter, and then the 4% limit to be?
Yeah, it's true. It's this is also the case. Actually, yeah, one should look at exactly what is the H upon R in these hotter disks. Yeah, you're right. So. Another issue which is not really related to that, but is worth keeping in mind, that that actually these masses are really the masses in the outer disk. And Hartmann in the last workshop that we had, he again made some suggestions that maybe the surface density profile might be a bit steeper than what we think, so that most of the mass is actually hidden from our side. But this doesn't really apply to this kind of estimates, but it's worth keeping in mind, and I'll come back to that later on. Okay, so having said that, let's have a look at what is the dynamics of self-gravitating disks. I'm sure, well, most of you will be familiar with the things that I'm going to say now, because the main point is that actually all of the conditions that I've described before only address the issue of the linear stability. Once the disk is linear and stable, we have to understand what is the behavior once the instability becomes nonlinear. So we have to investigate numerically the evolution of these instabilities in the nonlinear regime. And this has been done in the last decade by really several people. I've listed here a few. This is not exhaustive, probably. The main point which came out of this extensive list of simulations is the very important role which is played by the thermodynamics of the disk. In particular, starting from Gammi, it has been realized that one key parameter in this business is the cooling time. Actually, it's not really the cooling time in itself which is relevant, but it's really the ratio between the cooling time and the dynamical time in the disk. So for the rest of the talk, when I speak about the cooling time, I will rather speak about this dimensionless parameter, which is the ratio of Tcool over Tdyne in the disk. Well, I call that beta. Okay, so most of these simulations are, well, the relevant dimensionless parameter here to deal with is this beta. So why is that? Why is the cooling rate or the cooling time so important in determining the evolution of the instability? That's related to the process by which the gravitational instability saturates at a given finite amplitude nonlinearly. And in particular, this is all related to the process of thermal saturation. And this is easy to understand if one thinks about the Q parameters, which tells us in a way whether the disk is linearly stable or not. And from the fact that Q is proportional to Cs and therefore is proportional to the square root of the temperature. Now, once the instability sets in and develops nonlinearly, it can feed the energy back into the equilibrium state and therefore stabilizes and gives a stabilizing effect to the disk. So basically, this process works as an effective thermostat for the disk. If the disk is if this cools down and there is no other source of heating, Q is going to go down until at Q of order 1, instability will set in, heating turns on, and therefore Q grows to make it stable again. It's really like a thermostat. And if your thermostat in your room works, you expect that the room will always be close to the value that you set in the thermostat, okay, the threshold value at which the heating turns on. Therefore, we should expect that if this thermostat process works, then the disk will always stay close to the value that we set in the thermostat, which is the marginal stability value, which is a number of order 1. Okay? However, in order for this whole process to work, we need the cooling time to be not faster than the dynamical time, which is the time scale over which the instability develops. Otherwise, there is no way in which we can keep the disk warm. So we expect a change in behavior when beta is of order 1. The exact number needs to be determined, but we expect to see a change in the overall evolution of the disk from going from large beta to small beta. And basically, this has been known since Gammi, that if you have short cooling time, the outcome of the evolution is fragmentation. And the actual threshold varies a little bit depending on the simulation, on the simulator. So Gammi in his 2D local models set the threshold at 3. We find something more closer to 5, and it does depend on a number of of things. It does depend on the ratios of specific heats in the disk. It depends also if, on whether the disk is, on whether the cooling is dependent on temperature or not. We have investigated that as well, and Johnson and Gummy did. However, I'll just show you a simulation of one of these, of the evolution of one of these disks with beta equal 4, which is below our threshold. So this is expected to fragment, and it does. But initially, the disk is hot and with no structure. As it cools down, it develops a spiral structure. But after a while, this spiral structure breaks up into a number of clumps. This is all gas, I should say. Okay.
Giuseppe, is that unit at the side? Is that in astronomical units?
No. All these simulations are scale-free.
They're scale-free.
They're all scale-free. Okay.
Beta is constant throughout the disk, is it?
Beta is constant, exactly. So there is no preferred scale. So you can scale it up. Okay. Okay, that's the case for low beta. What happens when beta is larger? Now that's exactly the same simulation as the one that I used before. Really exactly the same. I should have mentioned, I didn't, that all these disks have a mass ratio of 0.1. So the disk mass is 0.1 times the central object mass. Now that's the same simulation, exactly the same, but now we have raised beta to a larger value, which is 6. Now that's above our threshold. And if we let this go, actually I'm going to let it go for a while. And basically what happens is that initially it looks pretty much the same. The disk cools down, develops a spiral structure. But the main point is that for as long as we have been able to run this simulation for, nothing happened. So we had a spiral structure which developed, saturates at a given amplitude, and didn't lead to any fragmentation. And we have run this for really many thermal timescale at the outer edge of the disk. So this has run for quite a long time. And you can see that basically it reaches a quasi-steady state. Obviously, the density in the disk will evolve secularly, due to the outward transport of angular momentum due to the spiral structure. But apart from that, you see, you can keep looking at that for as long as you like. Nothing is going to happen. Another interesting plot that's related to this simulation is a plot of the Q parameter. So that's the same simulation as before. So that's Q as a function of radius. The green line is the marginal stability, Q equal 1. And that's the initial profile of Q. So initially we had our disk which was stable at all radii, so very large Q. But since we have cooling, as you're going to see, Q is going to drop. And indeed, that's what happens. Because of cooling, Q goes down, but it doesn't go down indefinitely. As soon as it hits more or less 1, the spiral structure sets in, it provides heating, and it prevents Q from dropping too much below unity. And indeed, here you can see very nicely how this process, this thermostat process that I was describing before, really works in a very nice way. And at the end of the simulation, you see how close to unity our disk stays. It's really amazingly close to unity, actually. So it's I think in the end it's something around 1.1, 1.2. Okay.
Driving Q up at the inner and outer edges?
These are just boundary effects, essentially. So that's the surface density. Here we have a sink. So basically the surface density goes down here and goes down there. So that's.
Do you expect Q to go up if you're sinking, if matter is falling into your sink in the center?
Sorry?
Would you expect if you're actually draining mass into the center?
We do drain mass in the center.
Why
So
doesn't
we have a
that make
sink here.
Q rise.
Sorry?
Why doesn't that make Q rise over time then?
It does.
In that region.
Yeah. Okay, so that's what we see. However, we can do more about that, because once we have established this self-regulated thermal equilibrium, so the gravitational instability is saturated thermally in all these simulations. Actually, we can do something more, because clearly in this regime, what happens is that the heat which comes from the dissipation of these spiral waves balances the cooling. So it's obvious that the amplitude of the waves at saturation must be related to the cooling rate. And the faster we cool, the larger the amplitude of our spiral waves should be in order to balance the cooling. And indeed, that's exactly what we see. So that's a plot of delta sigma over sigma in our simulations versus 1 over beta, which is effectively the cooling rate, and we can see that it rises as the cooling becomes larger. And indeed, we find that delta sigma over sigma is very close to 1 over the square root of beta. Actually, this fact that this delta sigma over sigma is close to the square root of beta, well, the square root to the minus 1 of beta, is quite natural. If one thinks that basically what we are setting up is an energy balance, and the energy is related to the square of the fields, of the perturbed fields. So basically, that's the cooling rate. And if you want to balance that with the heating rate, which must be proportional to the square of the fields, then you automatically get this kind of scaling. So yeah, so that's actually quite nice. So we can predict, based on what is the instantaneous cooling rate in the disk, we can predict what would be the amplitude of our spiral structure. There's another thing which is actually very, very interesting that came out from, well, all these things can be found in this paper by Peter, which is now published. So what we have done, we have also computed the pattern speed of our waves as a function of radius, and in particular, we have computed the Mach number, the Doppler shifted Mach number, and that's seen here. So that's the Doppler shifted Mach number for as a function of radius for a number of simulations with varying beta and with varying mass ratio between the disk and the star. And well, what's really amazing here is how close this Doppler shifted Mach number is to unity, regardless of the cooling imposed and the mass ratio. So basically, what really is happening here is that these waves propagate. As soon as they become sonic, they dissipate and they release energy to balance the cooling that we impose. And actually, that's also quite nice, because you can see it's quite easy to work out what would be the entropy change in an almost sonic shock, and you can relate that to the density change. And it turns out that again, the condition of sonic shock really tells us again that delta sigma over sigma should be proportional to the inverse square root of beta. Okay.
Is the heat input just from shocks?
Yes.
You could also have turbulence, subsonic turbulence, which goes into efficiency.
Okay. Yeah. You're right. So basically, in the code, the only source of heating is due to artificial viscosity in the code. Okay. So that's the only. Well, obviously we have PDV work, but that's the real source of dissipation comes from the artificial viscosity, which does play some role also if in the slightly supersonic. Well, that's within the SPH code. So even if you have slightly supersonic waves, you do dissipate a little bit that through artificial viscosity. So, but we've been very careful in trying to keep the artificial viscosity low enough so that it really should pick up only close to shocks. Another issue which is very important is whether the overall behavior, or the long scale, the secular evolution of this disk can be described within a local model, or it cannot. So the global effects related to self-gravity are predominant. Again, this is something that I think, well, Caroline mentioned yesterday. Really, the ones that have described that in the first place were Balbus and Papaloizou, and now I'm trying to, and we have discussed this also extensively in our paper. I will try to rephrase the arguments of Balbus and Papaloizou in a way which I understand. Basically, the origin of the fact of whether you can describe it in terms of a local prescription or not is related to that. We all know what is the relationship between the energy density and the angular momentum density in a wave, in a density wave, which is, so if that E is the energy density and L is the angular momentum density, then the two are related by the pattern speed, omega p. If you generate or dissipate one such wave, you're going to exchange energy with energy and angular momentum with the background flow, but obviously the ratio of the exchanges rates is also in terms of omega p. So if you simply differentiate this with respect to time, and if you produce or absorb a wave, the ratio of power to torque produced in this process is also in terms of the pattern speed of the wave. Now, if you have a local process, a viscous process, the relation between power and torque that is provided in this case, that's related through omega, the local angular velocity of your disk. So basically, you can see that these two are different unless your waves are close to corotation. So basically, the farther away, so if the wave is allowed to propagate very far from corotation and is absorbed very far from corotation, then the behavior will be non-local. While if it's always close to corotation, then this a local description is fine. We can calculate that. So basically, a simple way to calculate how non-local we are is to measure this parameter, which we call psi, omega minus omega p over omega. And again, also this parameter is essentially set by the sonic condition, because you can clearly say that if the wave dissipates when they become sonic, basically this difference over omega must be of order of Cs over V phi, which in hydrostatic equilibrium is of order h upon r. So basically, we can conclude that to the extent that h is much smaller than r, psi should be much smaller than r, much smaller than 1, and therefore the behavior should be well described in terms of a local process. And indeed, actually, that's what we find. So as this is psi as a function of radius for various simulations where we keep the mass ratio between the disk and the star fixed, but we vary the cooling rate, and that's around 10%. But there is a dependence on the disk mass. So as we make the disk mass larger, this ratio becomes larger as well. Okay, so the more massive the disk is with respect to the star, the less local the overall process will be. Okay. However, in the case where we have relatively small h upon r, then it would be possible to construct local viscous models of disk evolution, even if the evolution is driven by self-gravitating disturbances. This indeed has been done recently. There are a couple of papers which address this issue, one by Clark and one by Rafikov. I'm going to come back to these models at the end of the talk. So let's now come to the second part, which is what happens to the solid. So now we have discussed the behavior of the gas in these disks. What happens to the solids? And yes, again, I don't need to spend too much time on that. We all know that gas drag is very effective in bringing particles to pressure maxima. In a laminar disk, this produces a very fast migration, and well, the radial velocity Vr is this one, and is related to the ratio between the stopping time and the dynamical time in the disk. And the maximum velocities occurs when omega ts is of order 1, which is around meter-sized objects. And the maximum velocity that you get, the maximum radial velocity that you get, is related to the steepness of the pressure gradients. Okay. Yeah. So it's and it's been well known. I mean, again that if you have a pressure maximum, then this is very efficient in trapping meter-sized particles into that. Actually, I think it was originally proposed by Hagigipur and Boss. Yes, Duris and et al. Also showed it numerically in 2005, but I think that the first one to really show that this process works numerically was actually us in 2004. What we have done is we have run a number of SPH simulations with two components. So we have the gas and the dust, and we just placed a single size dust, but we varied. We run several simulations varying the size of the solids that we put in. So just to show you some pictures of the evolution of these systems, that's the gas, which shows the usual spiral structure. And then if we put two different sizes of solids, then we get these two pictures here. So we can see that when you get close to meter size, you have really, the particles do concentrate very strongly on the peak of the spiral arms, much more than in the case of 10 meter size, where actually basically the solids simply follow the gas. So basically the gas to dust ratio is unchanged in this case, but is very much changed in this other case. We can be more quantitative about that. And this is shown here. So basically, this shows at a, so let's take one of our simulations and freeze it in time. Let's take a snapshot at one given time, and let's measure the distribution of this ratio here. This is rho over rho bar, where rho bar is the Roche density. So when rho hits rho bar, the solids are gravitationally unstable. And you can see that for 10 meter size, nothing really happens. The peak is well below the Roche limit, while for the 50 centimeter size, the distribution is squeezed to the to high densities, and indeed in a number of them, actually, the densities are high enough to be comparable with the Roche density. I should mention here that the Roche density is actually close to the gas density in these simulations because the gas is self-gravitating. All these simulations did not include a number of things. They certainly don't include the back reaction of the dust onto the gas. So here there is no streaming instability operating. So basically what we find is that we can get to Roche densities without any streaming instability. And that's just because our disks are very massive to start with, and their densities are high enough. They're self-gravitating, so you just need to get to the gas density in order to be gravitationally stable. And these simulations here didn't even include the self-gravity of the particles. Okay, so they were just a passive medium in our simulation, so we couldn't really see the actual fragmentation of the or concentration of these solids. But we then ran some other simulations, that is 2006, where we did include self-gravity in the solids, and we did find that actually the solids were concentrating on gravitationally bound objects. So the mass of these final gravitationally bound objects that we found in the solid is actually very hard to estimate numerically from these simulations, basically because of poor resolution. So I don't want to give you a mass because I wouldn't be able to tell you what would be the mass, because there are numerical resolution issues here. So yeah, so we can actually effectively form rather large planetesimals by this mechanism. But there are a number of questions to be answered. What happens after that? There is a problem which we again have investigated here in this paper by Breach et al. And the problem here is, what is the dynamics of these large planetesimals, which are now decoupled, which have become large, so they're not affected by gross drag, but how do they evolve in this highly turbulent self-gravitating disk? And this is very similar to what Richard has done in his MRI simulation. So he's done it in the MRI context. We've done a similar experiment for our gravitational instability model, and basically the results are the same. These planetesimals are excited to very large eccentricities. Basically, we find that overall they reach an equilibrium eccentricities of 0.07, 0.1. So quite large eccentricities are very easily excited simply because of the stirring due to the presence of this rapidly varying structure. So that's actually a bit of a problem because, significantly reduces the ability of further growth of these objects, and also these large velocities involved might mean that collisions between these particles might actually be disruptive rather than leading to growth. So this is actually so further growth is hindered due to the presence of the spiral structure. There is a further question that I would like to ask, and is, do this kind of, where in the disk, in which locations in the disk do these kind of processes work? Is there some special location where these kind of processes are more likely to happen or not? And in order to do that, I'm going to come to the last point of my talk, which is a discussion of these self-regulated disk models and how do they apply to the issues that we are considering here. So just to stop for a moment and summarize what we have learned so far. Particle traps in spiral arms are effective in terms of producing large solid bodies in the disk. The resulting planetesimal mass is going to be quite large, although I can't put a number on it. it's expected to be a very dynamically steered population of planetesimals because of the process that I just described. And that's expected to occur in the early phases of star formation when the disk is massive, so before a million years. But then, as I was telling you, another question is this process limited to some specific radial range? And the question is really down to how large a spiral perturbation can get in our disk. Because the simulations that I showed you before actually were just using a toy model for the cooling, in which way, basically, the delta sigma over sigma in these simulations was rather large. It was of order 0.1. So basically, we know that if you get a spiral structure with an amplitude of 0.1, yes, you can make it. But the question is, under which conditions can you get to this large perturbation due to self-gravity? Clearly, this is going to be in regions where the cooling is very fast. Okay? And in order to understand that, basically, what we need is a detailed model of self-gravitating disk with realistic cooling. And here is where the models that were developed by Clark and Rafikov come into play. Because if transport is local, and I've argued that if the disk is thin enough, then that's the case, basically, well, in thermal equilibrium, we know that there is a well-defined relation between the alpha, which needs to be provided by gravitational instability, and the local cooling rate. So basically, it is possible in these cases to construct models of self-regulated disk, which by construction have Q equal 1, where viscosity is provided by gravitational instability and is related to the cooling time in this way. Now, we know the temperature, we know the surface density, and we can therefore calculate what is the actual cooling rate, and we can construct our models for these self-gravitating disks in a kind of a similar way to what Caroline was describing yesterday, in a way. But these are all 1D models, just 1D radial diffusion models. And we can therefore identify various possible regimes for these self-gravitating protostellar disks. And the general picture that comes out of this modeling is summarized in this plot here. Okay, this is a bit of a messy plot which identifies the various possible regimes. So this is as a function of radius and m dot. So basically, for different accretion rates, steady-state accretion rates in the disk as a function of radius, we can identify various regions. Again, similar to what Caroline showed yesterday, the inner parts of the disk are going to be MRI active. But in the outer parts, there is a region which is going to be quasi-steady and dominated by gravitational instability. And outside, say, 50 AU, that's the regime where the cooling time is so fast that the disk fragments. So essentially, beyond, say, 50 AU, the disk fragments. Within a few U, depending on the accretion rate, the MRI is active. And then you have this intermediate region where self-gravity can provide an effective source of transport. Obviously, throughout this region, the effective value of alpha changes because the cooling rate changes. Okay, and just to guide your eyes, the typical accretion rates of class 1 objects are in this range. If you go down to the class 2 T-Tauri stars, then you're down that range. One thing that I should mention, that if you do this exercise and check what is the radial structure of the disk, it turns out that in this part where cooling is thus dominated, the density profile is quite steep, actually. You can analytically check that is r to the minus 9 quarters, which is kind of related to what I was saying at the beginning of the talk and to what Lee Hartman was boldly suggesting in the previous meeting, that at the end of the class 1 phase, it might well be that disks are very strongly centrally concentrated. Okay, but so basically that's the kind of picture that we got. The various lines that are shown here show the fragmentation threshold, and the reason why there are two lines is because in one line we don't take into account the effect of the fact that the cooling rate can be temperature dependent. If we do take that into account, this leads to an enhanced fragmentation well, very well, this is probably not relevant, but that's where the transition, well, here we are close to the gap, opacity gap, and that's been known by Johnson and Gamby, that close to the opacity gap, the strong temperature dependence can make fragmentation easier. So yes, so where do planetesimals form? Okay. Now what we can do is to check, because we have that, we have our model, so we can check at which radii the spiral arms are large enough, well, in terms of delta sigma over sigma, to produce effective concentration. So basically, solid concentration, where you can easily work out under which conditions solid concentration is effective, you have to require that the radial solid drift velocity is rather large. That's related to the scale over which your density changes. So we are imagining a situation where you have a sudden density peak with height delta sigma, which occurs on a scale lambda. Okay, so that's the radial velocity that you get in this case. And the time scale for migrating to the peak of the spiral is given by this expression here. And usually for this self-gravitating disk, lambda is of order h, so this is a number of order 1. And the lifetime of this feature is of order 1 upon omega. So basically, you would require this number to be not too small, because if this number is too small, then this time scale becomes long, and you don't have time to concentrate in the spiral arms. So basically, you have to require that delta sigma over sigma is larger than the number f, which is not equal to 0. It should be 0.1. Okay, so because yeah, this should be 0.1, because we know that for delta sigma over sigma of order 0.1, we were able to get concentration. So so we know that. So in which regions of the disk is delta sigma over sigma so large? So we can then take our model. This is just another version of the same plot that I showed you before. And basically, this line here marks the delta sigma over sigma equal 1 boundary in the disk. So basically, the region where this process is going to occur is this region here, which is essentially between 30 and 50 AU. So this process is only going to work at large distances, where the cooling rate is fast enough for the spiral structure to be substantial. So it's only between 30 and 50 AU that this process occurs, which is interestingly coincident with the location of the Kuiper belt. Now, what does this imply? Actually, I think that it's kind of interesting that we have in principle a mechanism to produce large planetesimals early on in the lifetime of these disks, concentrated in a narrow annulus between 30 and 50 AU. This is interesting, for example, if one considers evidences coming from debris disk, because there is actually some evidence for a large inner hole in the planetesimals distribution coming from debris disk studies. And that's based on the fact that there is an apparent increase in the brightness of this debris disk at a late time, at a late age of 10 to 50 mega years. And that's related to the fact that you have to wait, if there is an inner hole, you have to wait enough time until the collisional time in this outer part of the disk becomes important, and therefore you have the production of this of collisional production of the debris disk. So basically this can help actually in producing this kind of inner hole, if we assume that the further evolution of the further dynamical evolution of this ring is not significantly affected across the lifetime of the disk. Alternatively, another interesting aspect which is coming from that is that if we store a lot of mass in the, I should mention another thing, that actually it turns out that the mass of solids that we can put into large objects in this case is actually large enough to produce the amount of dust that is required from debris disk observations. So basically what we estimate we can collect here into large bodies is a mass of order of a few hundred Earth masses, okay, which is, I think, is quite right in order to get debris disk emission. Alternatively, I was saying, this thing could also be helpful in terms of retaining the millimeter dust grains during the Titari phase, which otherwise would be swept in. Yesterday, Keith mentioned this problem in his talk. However, in order to do that, actually, we should require, well, the submillimeter emission in T-Tauri phase is very large, so we should require the distribution of planetesimal sizes in this region to be very much steeper than what we think, and also we should require that the collisional times are a bit smaller, so it's not clear whether this applies or not. However, connected to this issue, yesterday Keys was mentioning that the presence of structure in the outer disk might be helpful in order to retaining the submillimeter dust. And he mentioned that in the next future, ALMA will be able to show us whether there is or isn't indeed this structure. So we tried to see, so one exercise that we did, and that's another thing that Peter has done, and that's just in preparation, so I don't want to spend too much time in discussing that, but we asked what would our disk look like through ALMA. And so basically we constructed a number of fake ALMA images for our disks at different wavelengths and with different spatial resolutions. So these are the parameters that we take. So a disk which is 50 AU in size, mass ratio of 0.1 around the 2 solar mass star, at the distance of torus for a 10 hours integration time. And so you can see that at 33 gigahertz, so short frequencies, basically the resolution is not, the minimum beam size is too large in order to see any structure, so it's all the whole of the structure is blurred out. However, when you go to higher frequencies, you get smaller, finer resolution, but the sensitivity goes down, so you don't get so much photons. So at 900 gigahertz, you don't see nothing. But there is an intermediate, region where actually, some spiral feature are would be seen through ALMA. So that's really quite encouraging. If ALMA comes online, we might be able to see these things. So here to my conclusions. Class 1 disks, I think, are likely to be gravitationally unstable. And the evolution of gravitational instabilities will generally lead to fragmentation only in the outer parts of the disk. Within 50 AU, we're going to have a prolonged period of self-regulated behavior, which leads to sustained angular momentum transport, which might bring the disk into the T-Tauri phase, possibly with quite a steep density profile. The spiral arms were the first sites to be identified as optimal particle traps for the formation of planetesimals, but we have shown that this process only works in the outer disk, say between 30 and 50 AUs. And this leads to the rapid formation of solids in an annular region, which is possibly consistent with the observation of debris disk, and its location is close to where the Kuiper belt is. And that's it.
So I suggest we have 10 minutes of questions and discussion on this particular talk before we move to have a more general discussion. So, any questions?
I just had a general question about how you can sustain the self-regulated state for, say, 1 million years. In the simulations you showed, I'm not sure if those actually went to 1 million years.
No, obviously it didn't. It's much shorter than that.
But there are two effects then. How would you prognosticate what they would do? Because that drive you away from steady state. And one is the accretion to the center, which would drain enough matter out eventually that over most of the disk Q would rise. Other quantities above the surface density were more or less fixed. And then the other effect is your spirals, which are dissipating through weak shocks, would dissipate. And then would you need more spiral waves to keep that process going?
Okay, so there are two issues here. First of all, yes, obviously, over a viscous time scale, the disk will evolve. Okay, and clearly, this is certainly going to be the case. But the viscous time predicted here is of the order of a few million years. It's the standard viscous time in the disk. The level of alpha that we get is of order 0.01, something like that, 0.1 maybe. But still, it's okay. So yes, I believe there is going to be viscous evolution in this disk, which will lead to the going out of the self-gravitating phase within a viscous time, which I agree. About the second point, whether the dissipation of the waves, yes, clearly they do dissipate, but they keep reforming because of the cooling. The disk is cooled, so even if you dissipate, then this energy is removed by cooling, so the disk is always close to marginal stability, and some modes will always be unstable.
The turbulence that you generate is close to sonic. Couldn't this be in danger of destroying the dust before they have a chance to
In danger of?
destroying the dust before it has a chance to accumulate. The particles will collide at high speeds.
Yeah, obviously, yeah. This might be the case. One should,
Have you measured the relative velocity between dust particles?
That's interesting. We tried. It's interesting because indeed there is a little bit of coherence. I mean, these particles do tend to collect coherently within the spiral structure. So there is some degree of coherence which does lead to a smaller velocity dispersion than what you would expect. Again, it's a bit hard to estimate it numerically because there is numerical noise which prevent us to measure really small velocity difference. But yeah, in principle.
Like what are the velocities do you get?
Well, typically, okay, I can tell you the number, but I don't want to make a big deal out of it because I'm not confident that this is not independent of resolution, for example. But what we get is typically, for the solids, a tenth of sonic. Typically, but I'm not sure. It could be smaller than that. I mean, there is particle noise which prevents us to measure smaller velocities.
Quite a few questions. So. Okay, Mark. We'll work around the room in this direction. Mark.
What fraction of the mass gets turned into planetesimals in this ring? Because you want it to be quite a small fraction, because otherwise.
Yeah, actually, that's a very interesting question, because if you judge from this plot that I put here, it would look that only a tiny fraction would be turned into planetesimals, only this upper tail. But this is actually not the case, because that's just a snapshot. So at a given time, only a small fraction of the particles are in these very high density regions. But we have measured, but at different times, different particles get into these high concentration regions. And we've measured that, and it turns out that roughly 8% of the particles experience this very large densities at some time, at some stage during the simulation. So it's actually, yes, quite a big fraction.
As you said, I mean, the best chance for gravitational instability to happen is in the early phases. And in the early phases, the disk is still accreting from the core, from the molecular core.
Yeah.
So this is an ingredient that is still missing in the model. What effects you think it might have on several things, including also on the range that you mentioned, the 30 to 50 AU range, where you may have that chance to form planetesimals?
Yeah, that's clearly correct, and I might refer you to the talk that we had a few days ago by Shantanu, who showed that indeed in this early phase of rapid infall, there is a way to keep the amplitude of the I'm just quoting what he found. Maybe you can correct me if I'm wrong. In this early phase where there is substantial infall, you rather than get into this kind of steady state, you get to this recurrent. Basically, there is a recurrent pattern when the spiral gets very strong and then goes down in amplitude. So this will affect the amplitude of the spiral. Exactly how would it change the various prediction of where the planetesimal will form is hard to tell. But yes, certainly there is going to be some effect.
My question was exactly the same as Lucia.
Same question? Okay, same answer, I guess.
No, I have a different one.
Hedge your bets.
Could you go over the conditions or requirements under which gravitational instabilities will produce this r to the minus 9/4 profile?
Yeah, it does depend on the specific cooling law. Okay, so I mentioned that this r to the minus 9/4 only applies to here it is. Only applies to this regime, which is more or less, well, you can't really see that. It's this band here where the cooling is dominated by dust grains. Obviously, if the cooling is different, then you will have a different profile. You can make up a new model. Yeah. So it does depend on that.
Yeah, I guess I had a really naive question and then another question. So let me ask a naive one. I just roughed out from your Q equals 1 expression, I just kind of worked out a kappa. And it looks like the kappa is really very, very small. Right?
Kappa being
the opacity. Is that what your kappa was?
Which kappa?
That's
the episcyclic frequencies.
Okay. Sorry. Okay, no, I knew that couldn't be right. Okay.
No,
so
also dimensionally one more.
Okay. So because in the cooling rate, a lot of these things can be strongly cooled. I mean, if the opacity, if the thermal opacity is large, you must be able to sort of derive a cooling rate sort of from a thermal opacity.
Yeah,
So
that's exactly what is done here.
that's what you.
That's exactly what is done here.
Good, great. So then, about this 30 to 50 AU spiral wave, does that transport enough angular momentum to like clear out a region in there, or what is the dynamical effect?
What do you mean clear out the region? I mean, clear out the region of what?
Just bring the gas in, just through the torques.
Yeah, basically it provides the torque, which is actually quite large. In these outer parts, the torque is quite large,
Right.
and it corresponds to a rather large alpha of order
Right.
point something, point a few.
So can you
Yeah,
bring
well-
a whole bunch of mass over a certain amount of time?
Yeah, it works more or less like a standard viscous disk with that given values of alpha. Yeah.
How long would you expect it to take?
Well, yeah.
I know you haven't actually run these very long.
Well, but this is going to be roughly the viscous time. So take the viscous time of a disk with an alpha of point a few is going to be a million year maybe.
A million years.
Yeah, alpha is a bit larger in the Titori phase. But
So I like your simulations where you were kicking around these large planetesimals / small planetary embryos around in your self-gravitating disk. So, but I wonder, did you check how good is your SPH approach for this? So in other words, did you check whether you can recover classical type 1 migration if you're going to a laminar disk?
yes, certainly we are not in the. Yeah, that's actually a good question. And no, we can't recover the type 1 migration, but the important thing is that that's not the regime where we are interested in. Actually, there, the whole scattering of the planetesimals is only due to the response to the pre-existing turbulence. I mean, the masses of the planetesimals that we put there is too small to produce any type 1 migration. So there is no real structure induced by the presence of the planet. It's very similar to what Richard did in 2005. So these are low mass planetesimals below the type 1 migration mass, but above the mass. So they are decoupled from in terms of gas drag, but they are not massive enough to enter into the type 1.
Giuseppe, I think the question was whether or not the lumpiness associated with SPH or the noise induces a certain level of eccentricity driving on its own, independent of these spiral structures. Is that what you were aiming at? I thought that was what you were aiming at.
Yeah, okay.
You have a particle just going around in the disk without these spiral structures, interacting with the particles through gravitational interaction. What is the natural tendency?
Oh, okay. I see whether they will be. No, okay. That's an. We didn't run such simulation. It's interesting, but yeah, Kathy, want to say something?
We did check that out.
We did.
I mean, yeah. I mean,
Okay.
SPH is lumpy, but it's not that lumpy.
Not that lumpy.
If it does, we should all go home.
Yes,
I forgot about that.
it's lumpy, but not that lumpy.
But certainly, I would doubt that it can reach 0.1 eccentricities that the one that you see with the spiral structure. So even if that's the case, then it's not. Yeah, it's true. Actually, I remember.
There you go. So, any more questions on this talk? Okay. Well, let's thank Giuseppe again for a very interesting talk.